Welcome back to Chemistry Exams Prep. This is Dr. Kulbhushan. This question is provided by Mr. Jorge Jimenez from New Mexico State University. He has provided three structures A, B, and C, and I have added two structures D and E to make the lesson more interesting. In this question, we need to figure out if the given species are aromatic, antiaromatic, or non-aromatic. So we have covered this type of question before, but this question is very interesting and very important. So what is aromaticity actually? So a compound is called aromatic if it fulfills the criteria of aromaticity and Haeckel's rule of 4n plus 2 pi electrons. So aromatic compounds are actually unusually very stable compounds, and that stability comes from the resonance delocalization of the electrons. And we know that when the charges are dispersed, the molecule becomes more stable. Molecule or species, either it's positively charged, negatively charged, or neutral species, when the charge disperses over the molecule, then it becomes more stable. And that's the reason that aromatic compounds are more stable. So this is the reason that benzene does not give any addition reactions. Instead, it gives the substitution reactions. So let's quickly review the four conditions that are needed for a compound to be classified as aromatic compound. So the first thing is that we need to see if the compound is cyclic. What it means is that there must be a closed loop of atoms. The atoms that are taking part in the aromatic structure, there must be a cycle of those atoms. And the molecular species, it must be planar. So a flat species would have all the atoms in it sp2 hybridized. So it must have all atoms as sp2 hybridized. Now there may be a heteroatom or just the carbon atoms. For example, in this structure here, D, there are only carbon atoms in the cycle. So are in species C, but species A has a heteroatom nitrogen here. So this part of the molecule is what is being considered to be aromatic, not the whole molecule. It is an important point to see that when we consider the molecule to be cyclic or planar, we consider the part that is taking part in the aromaticity, not the whole molecule. Because this part here, this group here, this carbon is sp3 hybridized, and yet the molecule is flat at the part where the aromaticity is involved. Now the third condition is that there must be conjugation. What it means is that the atoms that are making the cycle, the closed loop, must be sp2 hybridized, and therefore there must be p orbitals available for resonance delocalization. And the fourth condition is that the species must have 4n plus 2 pi electrons. So this number gives a magic series that involves the series that has 2, 6, 10, 14, 18 electrons and so on. And this series is generated when n's value is 0, it gives 2. When n is 1, it gives 6 pi electrons. When n is 2, it gives 10 pi electrons. When n is 3, it gives 14 pi electrons. And when n is 4, it gives us 18 pi electrons. So n is actually not the property of the molecule itself, but it's just a factor that gives us this magical series which is needed for species to be aromatic. Now these pi electrons, as we saw before, the pi electrons are the electrons that are in the p orbitals. So let's now quickly see and label each species as aromatic or antiaromatic or non-aromatic. So as we saw, species A, it has a flat structure, and the nitrogen here is actually sp2 hybridized. So the nitrogen can be sp3 hybridized or sp2 hybridized, but whenever the nitrogen or any other heteroatom is next to a sp2 hybridized carbon, then it takes the hybridization as sp2 in order to do the resonance. And that's the reason that this molecule, the structure remains planar. And the part of the molecule that is this aliphatic part, this is not flat, but we don't have to have this as flat part, because that can be in a three-dimensional, but the only part that needs to be flat is the part that is taking part in the aromaticity. So the species A fulfills all the 4 criteria. It is cyclic, it's planar, conjugated, it has 4n plus 2 pi electrons. In this case, it has 6 pi electrons. So therefore, the species A is aromatic. Now, if we have a look on species B here, so B has 2 heteroatoms. One is nitrogen, and if we forget about the oxygen for a second, then it would become, if there were a carbon instead of oxygen there, then it would be pyridine. And pyridine is aromatic because this nitrogen here is sp2 hybridized, and this lone pair resides in one of the sp2 hybridized orbital, and it has a p orbital that takes part in the resonance delocalization, the overlapping. All right, so now about this oxygen. So this oxygen is also sp2 hybridized, and the reason for that is again because this is next to a carbon that is sp2 hybridized, so it takes the shape of sp2 hybridized oxygen, which is a planar oxygen. So this species now is planar. It's a cyclic species, it's conjugated, and there are 4n plus 2 pi electrons. Now there are 6 pi electrons here that are taking part in the resonance delocalization, and that makes it an aromatic compound. The lone pair on nitrogen does not take part in that localization. It resides in sp2 hybridized orbital, and same way the lone pair of electrons on oxygen atom is also in a sp2 hybridized orbital. Therefore, this species is aromatic. Now, if we look at the species C here, This species is actually antiaromatic. Now, what is antiaromatic? So antiaromatic compounds are actually unusually unstable, just like the aromatic compounds are unusually very stable. These are unusually very unstable, and their stability, actually whether aromatic or non-aromatic or antiaromatic, these can be explained by molecular orbital theory. And so that lecture is for some another day. But the only difference between aromatic and anti-aromatic compounds classification is that the first three criteria are the same. So anti-aromatic compounds species are also cyclic. They are planar, there is conjugation, but there are only 4 n pi electrons, and the n is again 0 or an integer, positive integer, 1, 2, 3 and so on. And so when n is 0 again, so it gives us 0, and when n is 1 it gives us 4, and then it's just a multiple of 2. So when n is 2 it becomes 8 pi electrons. When n is 3 it becomes 12 pi electrons, and so on. So since we must have at least some pi electrons to have the resonance, so the 0 one doesn't work. The smallest antiaromatic compound must have 4 pi electrons, and that is cyclobutadiene. That's a very known antiaromatic compound. Now if we look closely on C, it has all carbon atoms as sp2 hybridized. There is conjugation, and it's planar molecule because of the being sp2 hybridized atom, and there are 4 n pi electrons, so therefore it is anti-aromatic. Now species D is if you look quickly, then one might confuse this as being anti-aromatic, because we just see quickly there are 8 pi electrons. But in this case we need to watch more closely, because this carbon here has one hydrogen atom, and that's why this carbon becomes sp3 hybridized. And once you have an sp3 hybridized carbon atom, its geometry is tetrahedral, so that makes the molecule unflat, and therefore this is a non-aromatic compound, because the compound is cyclic but it's not planar. And once it is not planar, then the conjugation is stopped there, so the pi electrons cannot move in a cycle, so the resonance is not complete, therefore it's non-aromatic compound. Now species E, again same way, it's got sp3 hybridized carbon there, and therefore this is also non-aromatic. Now we have seen some students drawing its tautomer or another form, which is phenol, and say this is aromatic. Well, that is aromatic. Phenol is aromatic, but when we consider a structure for aromaticity, it is the structure as it is, not what it could be. So in this case, when we consider structure E, this is non-aromatic, but its phenol form, when the tautomerization takes place, then yeah, it is aromatic. Alright, so to recap our lesson, The first thing we want to see for any species to be aromatic is there a cycle of atoms, and is it planar? All atoms are sp2 hybridized. Are there p orbitals available on each atoms that are taking part in the resonance delocalization? And is there number of electrons, number of pi electrons 4n plus 2, means are there 2, 6, 10, 14, 18 and so on pi electrons? If that is the case, then that species would be aromatic. If the first three conditions are fulfilled but the pi electrons are only 4n, then the species would be antiaromatic. And if one or more elements or conditions is missing, then the species would simply be non-aromatic. Alright, so if you have any questions, please let me know. Thanks for watching.